So welcome back. Today, having done everything about the ideal Fermi gas, we have looked at this ideal Fermi gas in the canonical formalism as well as in the grand canonical formalism. So we have looked at the T equal to 0, which is the degenerate Fermi gas, and we have also looked at finite temperature but close to T equal to 0. We have seen how mu, the chemical potential, depends on this temperature, how the internal energy depends on the temperature, and the specific heat depends on the temperature. In the current lecture, what we are going to do is we are going to study a relativistic Fermi gas at T is equal to 0, so that we can write down this as mc square 1 plus p over mc whole square half minus 1, and here I have taken care of the rest mass. I have subtracted it out from in this relation. So I want to study how this Fermi gas is going to behave at a T equal to 0. So before we go ahead with the calculation, let's just look at two limits of this. First of all, if you look at P over mc much larger than 1, you will see that epsilon is mc square. This is the term which dominates, so P over mc whole square, and then I have raised to the power half minus 1, which becomes mc square P over mc minus 1, which is just C times P minus mc square. This is your rest mass energy, as you already know, and this is the case of an ultra-relativistic gas. In contrast, when you have P over mc as much less than 1, then you have mc square. I can expand this quantity in the brackets in a binomial series, so that I'm going to have P over mc square and keep up to this order minus 1, which gives you mc square times half p square over m square c square, which gives you p square over twice m. So therefore this gives you the non-relativistic gas. And when you look at this energy expression, you are kind of doing both. Just have to figure out the limits when you finally want to know the results. So let's start with this. Since it's a fermionic system, I have eta is equal to minus 1, and therefore ln of q eta, just recall, was minus eta sum over k ln of 1 minus eta z e to the power minus beta epsilon, which is minus eta. In this case, for a fermionic system, I know that this is going to be ln of q minus which is going to be sum over k ln 1 plus z e to the power minus beta epsilon. We want to convert this sum into an integral over the energies, so that we know that sum over k will go as v over 2 pi cube integral of dk. And this integral, again, we can write down this as, in 3 dimension, this is going to be k square. We will look at 3D system only. Once you have this as 3D, I can rewrite this equation as v over 2 pi whole cube. Now you see that here the momentum is in terms of p. So I want to write it down in terms of p, which will give me dp p square v over 2 pi h bar whole cube, and I'm going to have a factor gv and a factor 4 pi that not over here, but a factor 4 pi that will come over here, so that ln of q minus becomes v over 4 pi gv. So let's over h cube integral dp p square ln of 1 plus z e to the power minus epsilon of p. I can integrate by parts. That's what we have been doing so far, so that this becomes gv over h cube p cube over 3 ln 1 plus z e to the power minus beta of epsilon p. This goes from 0 to infinity minus integral dp p cube over 3 divided by the derivative of this term, the log term, with respect to p. So that is going to be z e to the power minus beta epsilon p, and then I have z e to the power minus beta epsilon right, and then I have ddp of minus beta epsilon. It's understood that epsilon is a function of p. This term, as you well know by now, it's going to be 0, so I am left out with 4 pi gv over h cube. The beta factor comes outside, and this minus gives you a plus, so you have a beta over 3, and then I have 0 to infinity dp p cube z e to the power minus beta epsilon 1 plus z e to the power minus beta epsilon. It's understood that the epsilon depends on p, the momentum, d epsilon dp. Let's write down this in the form that I know: 0 to p dp p cube over z inverse e to the power beta epsilon plus 1 d epsilon dp, and this I know that I can write down this as 4 pi gv over h cube beta over 0 to infinity dp p cube np d epsilon dp. We have seen this in the standard results of a Fermi gas. So this is going to be your ln of q minus. The energy is going to be sum over k epsilon k average of nk, which is going to be 4 pi gv over h cube 0 to infinity dp. I will have epsilon of p there is going to be a p square, and then I'm going to have 1 over z inverse e to the power beta epsilon plus 1. So these are the two results that we are primarily interested in. If you notice, then you see I have not yet worked out the result for average of n, sorry, the total n, is going to be sum over k average of nk, and this will give you the same result that we obtained when we did the degenerate Fermi gas. So this is going to be 4 pi gv over h cube, 0 to infinity dp p square 1 over z inverse e to the power beta epsilon plus 1. Right? Now we are looking at t equal to 0. So that this implies that I have a Fermi sea, so all energy level up to the Fermi energy is filled up, and corresponding to this Fermi energy I know that I have a kf and therefore a momentum pf. So the idea is to figure out this momentum pf, and which I can do from this relation, right? So that would mean that n is going to be 4 pi gv over h cube, 0 to pf dp over p square. That gives me 4 pi gv over h cube pf cube divided by 3. So I have n h cube divided by 3nh cube 4 pi gv is going to be pf cube. If you look at this expression, then you see I can take some things out. 4 by 3 pi pf cube gv over h cube. Right? So this is the volume of a sphere of radius pf. And this essentially gives you the Fermi momentum pf. So that pf is going to be n by v. I can combine it into small n. So this n and this v I can combine into a small n. I'll be having 3nh cube divided by 4 pi g raised to the power 1/3. This result is identical to the value of kf which we got when we worked out the degenerate Fermi gas. In fact, you can clearly see that if I write pf as h bar kf and substitute this relation over here, then I'm going to have 3nh cube 4 pi g is going to be h cube kf over 2 pi whole cube, and you see h cube is going to cancel away. I'm going to have 2 into 2 pi instead of 4 pi, so 1 2 pi factor cancels to give me 2 pi whole square, so that kf is 2 pi whole square by 2 3ng, so this is cube 3n divided by g. This is 4 pi square, so this gives you 6 pi square n over g as kf whole cube. It's the same result that we have obtained before. The reason they are same is because the energy epsa p does not enter this expression anywhere. What enters is only the dispersion relation, and as long as since the dispersion relation is same, therefore one has the same expression. So now I have ln of cube minus, which was 4 pi gv over h cube, and then I had beta over 3 dp p cube np d epsilon dp. Strictly at t is equal to 0, I know that I have np is going to be theta of p minus Pf, which essentially means that all momentum levels from 0 to Pf are filled, just as we had seen for Fermi gas at T, degenerate Fermi gas at T is equal to 0, so that essentially this limit which goes from 0 to infinity is now replaced by beta over 3 0 to Pf dP P cube d epsilon dP. This is strictly at T is equal to 0, and we will use this later on. The energy is going to be 4 pi GV over H cube 0 to infinity dP P square epsilon as a function of P, and then you have average of NP, which again translates to 4 pi GV over H cube 0 to Pf dP P square epsilon P at T is equal to 0. One has to, please let's go back and just check whether we have done it correctly, otherwise we have to do it again. Okay, this looks right to me. Anyway, if we have made some mistake, we'll come back and correct it. So now before we go ahead, I have to take a look at this derivative, and I have to use this. And energy, the relation in terms of momenta was not very simple. We had 1 plus P over mc whole square, this raised to the power half minus 1. So we will make some substitutions to make our lives a little bit easier. So we go from a variable P to x such that P is mc sine hyperbolic x. And therefore, one should note that dP dx, which you are going to use frequently, is mc cos hyperbolic x, and 1 plus P over mc whole square is 1 plus sine square x, which becomes cos square x. This becomes cos square x, so that you have mc square cos x minus 1. This is the relation. D epsilon dP, which we are also going to need, is going to be d epsilon dx times dx dP. D epsilon dP is simply mc square sine hyperbolic x times we have calculated this becomes 1 over mc cos x. Please remember that sine hyperbolic x is e to the power x minus e to the power x minus 2. Cos hyperbolic x is e to the power x e to the power minus x by 2. If you have n sitting over here, so this becomes nx, 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 nx. So this you can use to calculate derivatives if you are unfamiliar with these hyperbolic functions. So with this in our hand, let's just first write down ln of q minus, which is 4 pi gv over h cube beta over 3 0 to xf, where xf is defined from this relation. So we will have Pf is going to be mc sine hyperbolic xf, which implies xf is going to be sine hyperbolic inverse Pf over mc. So this becomes dP P cube d epsilon dP, which we write down as 4 pi gv over h cube beta. Note that this is strictly at T is equal to 0. We are looking at the degenerate Fermi gas. So in this case we have the limit of Pf. We will write down the limit of xf only after we have made the change of variables. This is dp dx times dx, and this is p over, sorry, this is going to be mc sine x whole cube. D epsilon dp is going to be, let's look at this relation, cancels out, cc cancels out one factor, so that you have c of tan hyperbolic of x. So we will write d epsilon dp as sine hyperbolic of x divided by cos hyperbolic of x, so that this becomes 4 pi gv over h cube beta over 3 0 to xf dx, and dp dx is mc cos x mc whole cube sine hyperbolic cube of x, and then you have sin x over cos x. This cancels out. I have m4 and there is a c factor here that one should not miss. So m4, m times m cube is m4. So I am going to have 4 pi gv m4, and I have 3 plus 1. 1 plus 3 is 4, plus 1 more is 5. So I'm going to have c5 h cube beta over 3 0 to xf dx sine 4 of x. This is going to be ln of q minus the energy U is going to be 4 pi gv over h cube 0 to xf. Now we are going to straightforward do it. P square is mc sine x whole square, and then I have epsilon of p, which in terms of this is going to be, in terms of x is going to be mc square cos x minus 1. Now, so let's quickly write down dx, dp dx is going to be cos x mc whole square sine square x mc square cos x minus 1. One factor of m here, two factor of m here, so cube 4. So you're going to have 4 pi gv m4 c5, the same factor, h cube 0 to xf dx. Now cos x times cos x gives you cos square x sin square x, and then you are going to have minus sin square x cos x. So this is the internal energy of this gas. Now the point is, how do you integrate? It's a little bit tiresome, but one should be able to do it. And we will do this exercise. It's just try to see if you can follow the calculations. I mean, you can try to repeat these calculations at your own time. Sin 4x is e to the power x minus x by 2 raised to the power 4, which is, if you recall that your binomial expansion is x to the power 4 plus 4c1 x cube y plus 4c2 x square y square plus 4c3 x y cube plus y to the power 4. We're just going to use this one. So e to the power 4x, which is this term, plus e to the power minus 4x. 4c1 is 4 factorial divided by 3 factorial, which gives you a 4 here. X cubed is e to the power 3x, y is minus e to the power minus x, so you have minus x. Here 4c2 is 4 factorial divided by 2 factorial divided by 2 factorial. So 4 factorial, 2 factorial, 2 factorial. So 4 into 3 by 2. If you want to calculate, this is the exact formula, and you can see that this is actually 6. But x square is e to the power 2x, y square is e to the power minus 2x, so we are just left out with plus 6. 4c3 is again going to be minus 4. Here, of course, you are going to have e to the power x, e to the power minus 3x, and this already you have taken over here. So our bracket closes here, and then you have 2 to the power 4. 2 to the power 4 is 1 over 16. Now e to the power 4x, so let's just first write down this, and then we will minus 4. This is e to the power 2x plus e to the power minus 2x plus 6. Now these are exponentials, so I can equally write them as d dx of e to the power 4x minus 4x 1 by 4, right? Minus 4 d dx of e to the power 2x minus 2x divided by half plus d dx of 6 times d dx of x. It's that simple. So 1 over 16, this is where the trick lies. Since I'm going to integrate this, so if I write down as the derivative of some function, then it's much easier for me. The 1/4 I can take 2 inside to write down this as sine hyperbolic of 4x. Again I can take 2 inside to write down this as 4 d dx of sine hyperbolic of 2x plus 6 d dx of x. Nothing much you can do over here. So this becomes 1 over 32. Let's take the derivative out, the operator out, and 1 by 16 inside. So I have 1 by 32 sine hyperbolic of 4x minus 1/4 sine hyperbolic of 2x plus 6 over 16. If I am going to do it, cancel out by 2, then I'll have 3 over 8 times x. Quite an elegant result. Similarly, so therefore let's just first write down 0 to xf dx. This is going to be 1 by 32. So let me call this function, let's say g1 of x is integral dx 0 to xf d dx of g1 of x, which gives me g1 of xf. Let's look at the energy. Now I have two terms over here, 0 to xf dx cos square x sin square x minus I have sin square x cos x. Yeah, so let's look at this. So I have 0 to, so here let us do the calculation, cos square x sin square x. This is going to be e to the power x plus e to the power minus x whole square times e to the power x minus x whole square. So which is going to be e to the power 2x. I was tempted to just write it down as e to the power 2x minus e to the power minus, sorry, this has to be 2 whole square, this divided by 2 whole square. So overall you have 1 by 16 times e to the power minus 2x whole square, because this you can write down a plus b times a minus b whole square. So you have a square minus b square whole square, and this is going to be 1 over 16 e to the power 4x plus e to the power minus 4x minus of 2. So again one writes this down as d dx of e to the power 4x minus e to the power minus 4x 1 over 4 minus d dx of, so 2 times x. So I have 1 by 16 half d dx of e to the power 4x minus e to the power minus 4x divided by 2 minus twice d dx of x. So I will have 1 over 32. Let's take the d dx outside. Sine hyperbolic of 4x minus 1 by 8 times x. So this is the integral. So therefore 0 to xf dx cos square x sine square x. Let's call this function as g2 of x. Then I'm going to have as simply g2 of xf. This is easy. 0 to xf dx sine square x cos x. Let's just change the order over here to write it down as cos x sine square x, which means 0 to xf d of sine hyperbolic x sine square x, and this is going to be sine hyperbolic whole cube xf 1 by 3. So this integral then evaluates to 0 to xf dx cos square x sine square x minus sine square x cos x is going to be g2 of xf minus 1/3 sine hyperbolic cube of xf. That is the final answer. Good. So it's a very tedious algebra, I agree with you, but let's go ahead. Since we have come so far, let's push it forward a little bit. ln of q minus is going to be 4 pi gv over h cube m4 c5 beta over 3, and the integral was integration of dx sine hyperbolic 4 of x raised to the power 4 of x, which we had was g1 of xf, and u, the energy, was 4 pi gv over h cube m4 c5 g2 of xf minus 1/3. I'm going to have sine cube of xf. Well, I can write down this as 4 pi gv over h cube 3h cube, since this also has a factor 3, and then I'm going to write down this as 3 times G2 of XF minus XF, where G1 of XF is going to be 1 by 32 4XF, and then I'm going to have minus 1 by 4 sine hyperbolic of 2x, and I'm going to have plus 3 by 8 of XF. G2, we will write down 3G2 of XF is going to be, this is going to be multiplied by this, so it's going to be 3 over 32 sine hyperbolic of 4XF minus 3 by 8 of XF, and let's call this together as G3 of X, which is equal to thrice G2 of XF minus sine cube hyperbolic cube of XF, so that I have the result 4 pi GV over 3H cube G3 of XF. That's it. So far so good. A little bit more algebra is left out, because what I want to do now is I know that PF is going to be sine hyperbolic this over XF. So I know this. So let's call this YF. So I want to express all this 4XF in terms of XF, because this is the primary variable of concern to me, which is YF and sine hyperbolic XF, which essentially, because in the very beginning of the class I had seen that PMC much less than 1 corresponds to a non-relativistic gas, and PMC much larger than 1 corresponds to an ultra-relativistic gas. So I will be looking for the limit of YF much less than 1 and YF much greater than 1. What is going to be the behavior of this function and this function? But before even we do that, essentially I have to express this 4XF and 2XF in terms of sine hyperbolic of XF, and that is not very difficult to do. So sine hyperbolic of 4x is going to be twice sine hyperbolic 2x cos hyperbolic 2x. This you can further break down as x cos x. Cos hyperbolic of 2x is going to be cos square x plus sine square x. If you want to write down predominantly in terms of sine square x, you are going to just as cosine double angle formulas to sine, except that one the sign changes. Sine square of x cos x sine hyperbolic of x, which is 2x sine hyperbolic x cos hyperbolic x plus 4 sine hyper cube, and then you are going to have cos x. So this becomes your sine x, and sine 2x is going to be 2 sine hyperbolic of x cos hyperbolic of x, right? So you can do this, and In terms of these formulas, if you just do it, then sin 4x becomes a of yf and 0 to xf dx. I had cos square x sin square x minus cos x sin square x, which was the expression which entered for the energy. I will call this, so this is going to be 1 by 8 ay and this is going to be 1 by 24 b of yf, where your a of yf is going to be square root 1 plus y square twice y cube minus 3y plus 3 sine hyperbolic inverse of y. So we will write down this as a of y. B of y is going to be B of y is going to be 8y cube 1 plus y square minus 1 plus a of y. So little bit complicated expression, but we have come to the fag end of this exercise. And just we are done with this and we are left out with little bit more steps. So one should note that beta PV is going to be ln of Q plus. So that I have the expression beta times pressure times volume is 4 pi GV M4 C5 HQ beta over 3, and then I had 1 by 8 of A of YF, and the energy was 4 pi GV M4 C5 over H cube 1 over 24 B of YF. So this clearly simplifies to the 4 gets cancelled over here to give you pi GV M4 C5 divided by 6H cube beta A of YF, and this is also going to give you pi GV M4 C5 6H cube B of YF. So that the thermodynamic pressure therefore takes care of the volume factor. So let's just use this quickly to write down thermodynamic pressure of this gas is going to be pi GV M4 C5 over 6H cube. The beta beta cancels out. I will have A of YF. So the V also cancels out over here. So you have only pi G. And this is the final expression that we have been trying to do, where AY and BY are complicated functions which are given over here. But let's just check whether we have come at the right result. So I'm interested in YF much less than 1. What happens to A of YF and B of YF? Here I have this sine hyperbolic inverse of x. So I am going to use the expression that sine hyperbolic y is going to be log of y plus square root 1 plus y square. This I am going to use in the two limits. I will not work out the limits, but I will just write it down it is very easy. So for y very less than 1, this is 8 by 5 y to the power 5, and then you have 4 by 7 y to the power 7 plus higher order terms when you have y much less than 1, and you have b of y is going to be 12 by 5 y to the power 5 minus 3 by 7 y to the power 7 plus higher order terms. This is the first expansion that you are looking at. For y much larger than 1, ay this quantity is going to be, we will use an approximate sign over here since this is an asymptotic expansion. Twice y4 minus twice y square for y much less than 1, and by is going to be 6y4 minus 8, sorry, this is cube, no, this is y square, and this is going to be cube for y larger than 1. And this means that if I look over this expression for these two, for the first limit I have u as pi gv over 6h cube, b of yf, right? I had this expression for u, b for yf much less than 1 is going to be 12 over 5 yf to the power 5, and the pressure is going to be pi g, sorry, I have missed out the M4C5, it's going to be pi g M4C5. In this expression, let's take the volume to the other side so that it's become clearer, more easier to handle. I'll have 6h cube, and it's going to be 8 over 5 yf to the power 5, right? So 2/3 times u over v is going to be pi g over M4C5 divided by 6h cube yf raised to the power 5, 2 by 3 into 12 by 5. Does it help? Now from this expression, if you see, if I multiply this by 3 by 2p, this is going to be pi g M4C5 over 6h cube times, there is a yf raised to the power 5, and then I have 3 by 5 times 8 by 3 by 2 times 8 by 5. This gives me a 4. 3 times a 4 is 12, and you have the result pi g M4C5 yf raised to the power 5 6h cube. You have 12 over 5. Now you clearly see that this factor is same as the factor over here, so that you know that 3 by 2 pressure is going to be u by v, which is the case for a non-relativistic gas, as we have seen. So once again we have done, everything is consistent. You should also know that the pressure is proportional to Pf to the power 5, just as we found out when we did the degenerate Fermi gas. Now comes the other limit, yf much larger than 1. And then you have u over v, which is going to be pi g over m4 c5 6h cube, and then I have 2 times yf raised to the power 4. The pressure was pi g m4 c5 6 times h cube, and this was 6 times yf. Now in the opposite limit of yf much larger than 1, let's look at ay. Ay is leading term is 2y to the power 4, and therefore pressure is going to be pi g m4 c5 over 6h cube 2 times yf raised to the power 4, and u by v is going to be pi g m4 c raised to the power 5 6h cube times 6 yf raised to the power 4. From this, it is immediately clear, these two factors, that the pressure is going to be 1/3 u over v. As we expect for an ultrarelativistic gas, we also note that the thermodynamic pressure is going to be proportional to the Pf raised to the power 4 at T is equal to 0. So here also one notes that this is at T is equal to 0. Now you might want to wonder why did we go through all this trouble of doing this, but interestingly enough, this finds application in astrophysics, particularly in dwarf stars, white dwarfs. But that is for a more special field, so we will leave our discussion here at this point. You know how to handle such systems.